Hello, everyone. Thank you for coming to my talk. It's the second day, and I think it's the last one before lunch, right? So at least now you won't get sleepy, right? So, my name is Ignat. I work for Cloudflare, and today we're going to talk about sandboxing in Linux with 0 lines of code. So a little bit about myself. I do Linux at Cloudflare, so mostly Linux kernel. I'm passionate about security, cryptography, and system performance, and I enjoy low-level programming, so Linux kernel, drivers, bootloaders, and other scary stuff written in C. I'm not that popular on Twitter, but if you know me, you might know me from this video. I was the first one to compare Linux to Bentley. If you haven't seen it, go and watch it. Yep. But the topic of today's sandboxing will be seccomp, and how many of you have been here last year? Oh, not much. So like last year, seccomp topic was quite popular. We had a workshop and we had a talk, a nice talk, but it was like fundamentals. We will repeat some of the fundamentals here, but we will go deeper and we'll investigate what are the shortcomings of seccomp, and I will propose a tool how to overcome these shortcomings for enterprise use. Before we dive into seccomp, we need to understand system calls, and to understand system calls, we just want to review the basic software stack which we use today, right? Anyone runs bare metal here? Code bare metal. What does the bare metal mean to you, actually?
Heavy machine in a rack.
Huh?
Heavy machine in a rack.
Machine in a rack, right? But you still have an operating system, right? Because like 15 years ago, I was involved in IoT, and we called bare metal where you don't have an operating system. So you just run your code bare metal, where now it seems like we call bare metal if you do have an operating system but don't use virtualization or cloud. But yeah, but eventually, like at the lower layer, you always have some hardware. It can be real hardware, virtualized hardware, right? Then you usually run some operating system on top. Most of us run Linux, and some of us run inferior operating system like Windows and Mac OS. Yeah, and on top of the operating system, we have our applications, actually our business logic, which do the tasks we want, right? And this is where, if you read different docs, this is where the typical separation comes, which we call like the user space, where our applications run, and the kernel space, where the kernel runs. Yeah, simple, right? So this brings us to system calls. So what are actually system calls? So again, we have our application, our business logic, and we run on the kernel, and we establish that the applications don't talk to real hardware. The applications usually talk to the kernel, and the kernel provides a set of functions, or like an API, right, for the applications to communicate with it. And the applications implement their logic by communicating to the kernel through these APIs. So system calls is a kernel API. It's a well-defined API. It's a well-defined interface between the user space, the application, and the operating system kernel, and it has some number of benefits, right? So it provides you with hardware-independent abstractions. So your code doesn't care if it talks to a hard drive on SSD, or even if it's a network storage. You kind of use the same set of functions, and you can and the underlying hardware may actually change, but you will still have it. Also, the kernel provides you basic operating system services like file I/O, network access, and again, here you don't care if you're using Ethernet or Wi-Fi or token ring, whatever. Some basic functionality like time, sound, etc. Also, through this well-defined interface, the operating system enforces different access control lists or rules and permissions. So we can fine-grain define permissions that some applications are allowed to do something and access hardware, and some applications don't, and there are privileged operations, less privileged operations, blah, blah, blah. And also, because the kernel is this middle thing between the application and the hardware, it can provide the resource management. This is where the modern multitasking operating systems shine, where they allow you to run many, many, many applications all at once, right? So far clear about system calls? Easy, right? So what is seccomp in Linux? Seccomp is just yet another system call. It's one of these small boxes where the application can call into the kernel for some things. But it's a little bit special in a way. The system call allows an application to notify the kernel which other system calls the application intends to use, and sometimes more importantly, which application system call it will definitely not use. And when the kernel receives that information, the kernel now enforces this so-called system call policy on the provided by the application. And in a nutshell, it's basically a tool an application can use to confine or sandbox itself. And like I stress the word tool here because it's like seccomp is sandbox. No. If you go on man pages and people will trash you for that, they say like it's a tool to create sandboxes, but not the sandbox itself. So in this way, like what seccomp does, it's kind of like the application and the kernel establish a contract between themselves, and the application makes a promise to the kernel that it will use one set of system calls, but it will definitely not use the other system call. And then later, if application breaks this contract, the kernel is free to penalize it, right, for breaking the contract. And it kind of seems counterintuitive, right, here, that why would application do that, right? So like, if application does nothing, kernel will enforce nothing, and your application will never be penalized. Why would the application go for trouble for risking to be penalized just for this purpose, right? But turns out, like in normal business scale, when the application is working as it should, it's okay. You don't need that. But it's kind of a very effective technique for if your application is not behaving as intended. So let's see a very simplified example. So imagine you decided to develop a clock application, or alarm clock, right? And I don't know, I keep joking with people around here that like SQL is not a programming language, Python is not you are crazy enough to implement it in C, right? For whatever reason, it's just a simple clock. So what does the typical clock application need from the kernel, right? So it will run on the Linux, and it will need something. So the only thing really the clock application needs is to know the time, right? And this is where you can sandbox this application. You can establish this contract with the kernel saying, hey, I'm just a clock application. All I need is this one system call, get time of day, so I can show it to the user, right? And kernel says, okay, and yeah, later, your application kind of works, and it needs to know the time. It makes a system call to the kernel, get time of day, and the kernel, yeah, I mean, this is what we agreed before on, here's your time, okay? But what if suddenly, because you wrote it in the scary C language, your application was compromised, right? Somebody got like a code execution in your application, and they steer the execution of application into another direction, so they like harvest your home directory, your passwords, and what do they want to do with that? Like if somebody controls the application, they harvested the information, they wanted probably to send it to themselves, right? So they will direct the application to send it over the network. So they will direct the application to call the send system call. But this was not part of the contract. So now the kernel penalizes the application, kills the application immediately, and prevents your data leak, right? So who was on the panel yesterday, right? So in the panel yesterday, we discussed where the boundary lies between like application security and cloud security, and like the same problem is within the kernel and user space. Like, is the kernel responsible for security of running applications probably know, because by default, the kernel has no introspect what the application does. But what seccomp allows an application to actually communicate its intent to the kernel. So then the kernel has this context and it can act upon it. So let's see how you can actually use the seccomp. Who is familiar with uname command in Unix? Everyone is, right? So yeah, if you run uname, it will tell you your operating system and some auxiliary information, when it was compiled, like what architecture you have, etc. Right, but uname command, the underlying implementation, there is also a uname system call, which uname command uses. So let's actually try to write our own uname command using the uname system call. And this is complete application. You can actually copy paste and run it. And the gist is like one simple main function, and the gist here is we call the uname system call according to the man page. We obtain the information and we print it out. We print the operating system part of the information provided to the user. Quite easy. So we can compile this application and test that it works as we intended. So if you run it, you will see my operating system Linux. Now, if you're going to follow this guide, and you will see that it prints not Linux, stop following right now, because seccomp is a Linux-specific technology. If you don't get Linux, then it won't work for you, right? So now let's try to sandbox this application, right? We'll get the code, and before our main business logic, which is the uname system call, we will insert a call to the function called sandbox, and which implements our sandbox. And we can implement this function. It's quite easy, 2 slides, but you don't have to understand all of that. The gist is the following. Seccomp, the modern version of seccomp is called seccomp BPF, so you kind of implement your policy in the BPF programming language. So you can actually write your program, which implements your policy, and this is very scary stuff. And for the purposes of this example, we will not implement a proper policy. We will implement an incorrect policy to show that seccomp actually works. So from the boilerplate code here, the main difference is, the main important part is this. So what we tell in the policy that if the program tries to call uname system call, we'll actually prohibit it. So we will deny the program executing a uname system call. And also the default action, if we violate the seccomp policies, for the kernel to kill the process, but we can also ask the kernel not to do that. And in this case, we will ask the kernel instead just to return an error code from the system call. And we can even specify which error code we want. We call it enet down. Network is down, right? So yeah, we define our policy as a program. There are some auxiliary bits which are not important for this context. We just copy-paste it from the man page. And then we're actually calling the seccomp system call, providing our program. And from that line, the seccomp policy is enforced by the kernel. So now let's see how it works. We can recompile our modified program with our sandboxing function, and we can try to execute it. And then we see something like this. We see that uname system call fail, and the error code is network is down. And we definitely know it's because of our seccomp, because uname system call is just copying strings from the kernel to user space, and you don't need network for that, right? So you can, in normal case, you can never receive an error code inet down from a uname system call, but here it is. And in our case, what we did is we changed the execution of the application to its error path. So we're executing there. There are limited number of cases you want to actually return a custom error code, because if you're actually protecting from a compromised application, you want to kill it immediately, not give it a chance to recover, right? So you want to kill the application, but in some cases, particularly, you might find this useful. And in this case, we just, for visibility's sake, we just returned an error to the application. But as you just seen, writing seccomp by hand is hard, right? So it's a low-level assembly-like language. It's hard to write, to review, to debug, and to update. And like you've seen the listing for very simple policy which prohibits one system call. Imagine how that policy would look like for an enterprise service, right? And also you need to be aware of different low-level details. You need to understand the system call numbers. So even though the system call name may be the same across architectures, the numbers inside the kernel are different. For example, you name system call number on x86 is different from you name system call number in ARM64. So for example, if you transfer your program from x86 to ARM64, your policy might not be enforced properly because the numbers are different. And if you read through the man page, you also need to set some additional auxiliary bits like no new privileges, etc., etc., etc. As anything hard inside the Linux kernel, so like Linux kernel comes up with this really hard interface for something like this or IOUing or something. There is also like a library on top which tries to simplify it, and for libseccomp you have a library called libseccomp. So actually, to make it more simple, we can rewrite our sandboxing function using that library, and you see that there is much less code now, and it's much more manageable and readable. And what we do here is the important parts. We set the default action. So for example, what we say is that by default, we allow all system calls, right? And this is an important bit. Then we add a rule saying if the system call name is uname, this time we will not allow the application to continue. We'll tell the kernel just immediately to kill the application. Yeah, and then we load our policy into the kernels with this wrapper, and again, from that line, the system call policy is enforced, right? And here, we don't need to deal with system call numbers anymore. We can reference it by name. It's a little bit easier to manage. So let's see if it works. We can recompile our modified application, and because we're using a library now, we have to not to forget to link to that library. And we can execute it, and then if you're running on a bash shell, you will see something like that, but system call, because and we see no output, right? Because this time we didn't allow the application to continue. As soon as it tried to use the uname system call, the kernel killed the application. Yeah, this is well and good. So this brings us to no code seccomp. So in all the previous examples, we've seen that to sandbox an application with this seccomp system call, you actually need to modify the source code of the application. But how can you do it without modifying the application? And why is it important, right? Again, we kind of touched it on the panel yesterday. So who is a software developer here? Oh, yeah. So how many you software developers or security folks who talk to software developers start a new project with that mindset? Said, yeah, most likely I will write bugs and security vulnerabilities. So the first thing should I do is to sandbox my application, right? One? Oh, okay. I don't believe you. So the question is, yeah, right. This is the last thing people want to do when they write their code. And like on top of that, like not everyone writes in the C language and even understands the system calls. You will usually use some, I don't know, like JVM, and good luck figuring out like which system calls it uses like when you write your code. So the fundamental problem with seccomp that seccomp can only apply the rules or policy to the current process. So your process needs to apply it to the self, and it is expected that developers will sandbox their code themselves, right? And there is no external interface in Linux to apply seccomp's rulecy to on an already running process. On the other hand, we have like operators, sysadmin, security people that have almost no control over seccomp policy because they can't modify the code. And Also, like, like we don't only run code that we write, we have like lots of open source projects and sometimes even proprietary code. And there is no way to, and like the vendor will tell you that code does this, but like it might have like SolarWinds connectivity or something, it may do something else. So like there is no way to sandbox third-party proprietary application. So this is the gap, right? So like from one side, you have software developers who can sandbox their code, but are not kind of incentivized to do so. On the other hand, we have all these other people, security people, operators, sysadmins, SREs, who want to secure production, but don't have the ability to do so. So part of it was tried to address by systemd, the old favorite init system. So if you run your code through systemd, you can write a service unit file. In the service unit file, you can specify this directive called system call filter, where you can specify an allow list of system calls for your applications to use. Right? And it's surprisingly well documented. So it also provides a nice wrappers. It can group system calls in like collections. So if you need networking or file I/O, et cetera, et cetera. So let's see how it works. So let's again start with, so we will dump all our properly sandbox application and start with the non-sandbox application. With no sandboxing functionality, we can still verify it works. We can write a systemd unit file for it, but also we can simulate it with systemd run, which will generate one on the fly. So we can run our code through systemd, and we can also verify it executes properly. So we see the expected output, and also systemd helpfully tells that it's finished with a success error code. All good, right? So now we can ask systemd to actually sandbox it. So we specify the system call filter directive, and we specify uname system call, and the tilde in front inverts the allow list. So basically, by default, it's an allow list, but if we put tilde, it's kind of turns it into a deny list. So we allow everything except the uname system call, and if we execute that, we will see no expected output. We will see that, and the systemd helpfully tells that the application was killed with a signal. So working as intended, and here we didn't have to modify any source code of the application. Systemd also provides another directory called system call error number, where we can simulate the first type of policy we generated. So instead of killing the application, we can, through systemd, tell the kernel to return a custom error code, and if we execute that, we do see some output from the application, but we do see it go through an error path. So we see uname failed, network is down, and the application wasn't killed, but the exit status is 1, according to our source code. All good? It's nice, but it will be finished by that, but like we still have some time. So there is a small print. Systemd has a lot of small prints that you have to figure out. If you go into the documentation, you would see that regardless of what you specify in your allow or deny list, some system calls are always allowed. And this is a list of system calls. And what do you think is the most dangerous one here? Probably, yes?
execv.
Yeah, execv. Execv is dangerous. And probably it's natural because systemd needs to execute our other process. Probably it needs execv, right? But why is execv is dangerous? So let's go back to our toy clock application. And yeah, and we have our attacker, which kind of compromised and achieved like arbitrary code execution in the application. What is the first thing the attacker would do? In all workshops, like, who is pen testing here? What do you do in the first place when you got code execution? Oh yeah, you kind of yeah, you want to spawn a shell because you want to. It's very hard to control the application through a security vulnerability. You want to spawn a shell and do whatever you want, right? So you will usually execute a shell. So this way, execv call is quite dangerous if your application doesn't need it. So it's the first thing you want to block, right? But systemd doesn't allow you to do that. So to address this shortcoming, we developed an sandboxing toolset in Cloudflare to kind of help with that. So it's a toolkit to inject seccomp rules or policies into almost any process. And it kind of follows the systemd approach, but takes it one step further. And the toolkit contains two parts. So one part is a shared library for dynamically linked applications. And the second part of the toolset is a special launcher for statically linked applications. Everyone here knows the difference between dynamically and statically linked applications. Statically linked means basically all the libraries are in one big executable and doesn't have any dependencies, but dynamically linked will depend on system libraries, right? But the advantage of it, it can block any system call, including execv. And similar to what systemd, it's a no-code approach, so it works on any binary written in any programming language, and even if proprietary binaries, you don't have access to source code. And the best part, it's kind of open source on GitHub, you can go in that. At this point, you might be wondering, like, shell library, what the fuck? You said no code, like, shouldn't like library require you to link and like code against it? Well, generally, yes, but this shared library is special, and I'm going to show you. Again, let's go back to our example of non-modified myOS application. So you can basically, we still recompile it just in case, verify it works as intended. So to sandbox it through our toolkit, you don't need to link it to the library, but you need to somehow ensure that the library is loaded into the process address space. And you can usually do it with LD preload. So what you can do is you can actually preload our library from the toolkit, and through another special environment variable, which that library understands, you can specify your desired seccomp policy. In this case, we provide a deny list, and it includes one system call called uname, right? And we execute the same code. Notice we didn't recompile it, everything. It's like we're operating on the binary itself. We see some helpful output that we actually added the uname system call to the process seccomp filter. And we see no output from the application, and the shell helpfully tells us the process was killed because it violated the seccomp policy. LD preload is a little bit tricky. So it usually works well in most cases, but for example, there are specific cases like setuid applications where for security reasons LD preload is ignored, and it's kind of a little bit of a fragile, right? So for example, you can add LD preload to systemd unit file, so the systemd will preload the library for you, but you can actually mistype the path, and it will be silently ignored, and you will be thinking you're with the seccomp policy, but you are not. And again, the setuid binaries, what if you want to restrict ping or something like that? So what you can do is technically, you can patch your binary directly. So there is a handy tool called patchalf, and you can actually add explicit dependency into the elf file. So it will always be loaded, right? But again, we're patching the binary here. We're not touching the code. We're not recompiling any code. And after you do that, you can check that now our binary is actually from other system binaries. It also depends on our sandboxing binary. So again, no modification of the source code, and then we can just rerun it without any LD preloads, and we can just specify the system call filter, our deny list in this case, and it will work the same very well. This is all well good for dynamic libraries, but dynamically linked applications. But what about static link applications, right? If we recompile our application and link it statically, we can still verify it works. But if we try our dynamic library approach, it won't work, right? Because it's a static link application. There is no linking of external libraries during the runtime of the process, and our kind of policy is ignored. And for these specific cases, this is why we have the second part of our toolkit is a special launcher, where instead of doing the LD preload dance, you kind of similarly to how you would do it with systemd, you rerun the application through our custom launcher called Sandboxify. And again, but the interface is the same environment variables. We can provide the deny list through this environment variable, and we can see that the seccomp policy is now enforced. And so this is a launcher, and we see that the seccomp policy is enforced, and the application is being killed. So Cloud for Sandboxing tool is quite easy. Configuration via environment variables, so you can easily integrate it with your init system for production services. So the recommended approach is, of course, a seccomp system called allow, which will provide you with allow list of, and basically anything not in the list will be not allowed by the seccomp policy. Sometimes it's very hard to do that, so you just want to prohibit very dangerous system calls like execv or like memory mapping or something like that. If you can't generate a proper allow list, maybe you should just generate a deny list and basically just specify the dangerous system calls. There is also a third environment variable called seccomp default action, where you can actually ask the kernel not to kill the application if it violates the policy, but just log the violation. So we actually don't support custom error codes yet, but what you can do, you can set it, only one variable is supported here, is called log. So if the process is violating a seccomp policy, it will just log in the operating system audit system that the policy was violated. And it's very convenient to discover what actually system calls are being used by a proprietary application if you don't have any access to the source code. And the toolkit, as I mentioned, contains two parts. So it has a lib sandbox dynamic library for dynamically linked executables only. And basically, you need to preload the library into the process address space. You can use either LD preload, but you can actually patch the binary itself with a patch alf command. And we have the Sandboxify launcher, which is good both for statically and dynamically linked executables. And but you need to launch the executable through the launcher. All good? Any questions? You might have a question. It's like, why do the hell we need the dynamically linked application if we have the launcher, which is good for both, right? It's a good question. The reason is, and I'm going to tell you, because we still have time, I'm going to tell you. The reason is because it allows you to enforce seccomp policy at a slightly later time. And why is it important? So here's a 10,000 feet view of how any process starts on the operating system, regardless of the programming language. So when you start an application, you usually have two phases. You have the runtime init, and even stuff written in C have the C runtime, Go runtime, Python, whatever. And then your kind of main application logic kicks in, your business logic, right? So if you use the Sandboxify launcher, the seccomp policy would be enforced before the runtime init stage. But if you use the lib sandbox approach, the seccomp policy would be enforced after the runtime init. But why is it important, right? Like, what is runtime init event, essentially? Runtime, if you take a look at it, it's shitloads of system calls which are never used anymore in the main logic. So like if you strace, for example, a starting C application, you will see it will check a lot of files, tries to load external libraries, checks some like locale, does some weird stuff with memory, like maps memory, marks it's executable, blah, 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 right? And the difference is if you enforce through the libsec sandbox approach, you will only need, and you're doing it properly by providing a very tight allow list, you only need to include system calls from your main application logics, where if you do it through the Sandboxify launcher, you actually need to allow all the system calls both from your main logic and from the runtime immediate state. Otherwise, the application won't start. So let's actually see an example. So let's go back to our toy application. And this time, we will implement a proper policy for it. So what is the minimum required allow list for this application to run and complete successfully? And if you do some investigation and trial and error, you will see that you only need to allow 4 system calls. So execgroup, fstat, uname, and write. That's it. And the application executes successfully with no error codes. Instead, and this is a dynamically linked application. Instead, if you just try, without even recompiling, to rerun this application through the Sandboxify launcher to successfully execute this application, now we have to allow list much more system calls. And in fact, it's like 4 versus 13 system calls in the allow list. And bigger allow list is bigger threat surface, right? So in a nutshell, if you have a dynamically linked application, if you prefer to use the libsandbox approach, you will end up having much tighter access allow lists, system call allow lists, which will probably really greatly reduce your attack surface. Because most of the time, all these non-needed system calls are the most dangerous ones in the runtime init stage. Well, this is probably really it. So these are some useful links. The first is a link to the man page for the seccomp system call. The second link is a link to the GitHub project for libseccomp if you're interested in the library. The third link is a link to systemd documentations for the system call filter directive. The fourth link is a GitHub link to our Sandbox Toolkit. Please use it, please contribute to it, improve it, like provide reviews, etc., etc. And everything which I described today and even more is described in the Cloudflare blog post, and there you can copy-paste all the examples, try to run them yourself. So yeah, this is the blog post. Yeah, I guess that's it. Like, opening for questions.